So our first panel is the future of HPC software. We have a really good set of panelists up here. I'm going to let them introduce themselves. I asked them each to provide a slide saying a little bit about their background and what they think the biggest problem facing HPC software is. So we're going to start. We've got Mike Heroux from Paratools, Martin Schulz from TU Munich. Andy Warner was going to be our industry representative, but he was unfortunately snowed in. So we have replaced Andy with Christian from the governing board, and from Sandia and from HPSF. Christian's going to try to channel Andy in his answers today. He's going to try to be a little more angry and a little more British in his. All right. And let's see, we've got Brian from Livermore and Michela from UTK. So I'm going to start. I'm forgetting what order the intros are in, so I'm going to move forward and we'll see who pops up. So we got Martin first. Martin, does your slide have? Yes, it has. Do you want me to animate this as you go along?
Of course, we do animations.
Okay.
Why not?
Right. Yes.
All right. Thank you very much for the introduction. Hello, everybody. My name is Martin Schulz. I'm from the Technical University of Munich. I come from the HPC side. Been recently dabbling also a lot in quantum, and there's a good connection there as well. If we look at roles in the software ecosystem that Todd asked about, currently involved in several large-scale projects on the European side that are looking for production quality environments. We have one project on building an energy-efficient software stack and one building a quantum software stack, which are all maturing, and we're hoping to roll them out over the next couple of years. So that's one big connection to HPSF. And then also I'm the current chair of the MPI forum. And this is not software, this is a standard, but there's a lot of open source software obviously connected to that, and so I think the importance is here as well. Looking forward to issues, I separated into two. On the technical side, I think what we're seeing is a lot of very independent technology stacks coming up. We were going to talk about AI in the panel specifically, but there's a quantum neuromorphic. Each one has their own community, their own way of style of writing, their own ecosystem, different levels of maturity, different levels of standardization. But we all want them to work together, right? We need to have them to work together. This is one of those really big challenges, how to align them, how to combine them, get matching interfaces, and hopefully get to some kind of homogenization worldwide. And that also brings me to the second part, where the more strategic side, I think we're seeing a growing divide, actually, if we look at internationally, just from a political perspective. There's also new blockages in collaboration in there. There's a push for independent solutions, which of course doesn't help if you're trying to do an open source ecosystem. So I think organizations like HPSF can really help there, and hope we bring this out in the discussion as well. And also, of course, this is an old topic to raise the importance of stable software, right? So how do we transition research software? That's a big issue. And then also, how do we make clear to people who develop hardware that software is equally important? Because hardware you can touch, obviously you need 50 people for that. Software you can deal with 2 people in the room and you're done with it, right? And so kind of getting these prejudices, I think we need to work a little bit, because it also then translates to funding and so on. And so I think that's going to be a big issue going forward as well. With that, I'll hand to the next one.
All right, thanks. Okay, Christian, you're up next.
I'm up next, okay.
Yes.
Hi.
If you want to present from there, that's fine. Or
so I'm Christian Trott, right? I'm gonna try. I mean, at least I have also a European accent, like Andy. It's not quite the same one, and not quite as nice and sexy, but I'll try my best. I'm having a few roles, right? I'm here mostly as a HPSF board member. I've been one of the people who've been driving the foundation, initially, and have been on the board since then. I'm one of the leadership team members of the COCOS project, which is one of the big projects in HPSF. I'm on the ISO C++ standard committee, working mostly on the library working side, group side, and dealing with HPC, in particular with HPC kind of relevant issues in the ISO C++ standard. So regarding big challenges for HPC, which I see as the big challenges which are facing us, one of them is something I very much agree on with Andy, and he actually had slacked that to us. This is one of the points he wanted to bring up as well. Is I think we are a bit in the danger of having AI suck a lot of air out of the high performance computing community, right? Like very focused on there's lots of investment going on in that area, right? That's where the vast majority of all hardware investment goes right now, and vast, majority of all hardware deployment goes right now. And I think AI concerns in terms of like software development, what their frameworks are and etc. There is some overlap, right? But I think the HPC community has quite a bit more diverse needs than AI, right? AI is in some ways much more homogeneous and much more focused on very specific algorithms, very specific technologies, etc. And I think we're a bit of danger that we overlook how much HPC investment there is still required. Then I need to. What did I actually want to say? Because I only made these slides about 5 minutes before we started.
Do you want to stand here?
Yeah, I think one big problem is the further diversifying of hardware, right? Like we've seen that starting, but with all these AI startups, doing different types of hardware, that has been accelerating, and we need to figure out how to adapt to that. And when I think we still have a problem in HPC that HPC was a very kind of non-homogeneous marketplace in terms of like software. Everybody did their own thing. It used to be that every grad student wrote their own like HPC program from scratch, and I think that's not sustainable, right? With the complexity of hardware, complexity of tool chains we have to support, etc. That is a big problem, and I mean that's one of the reasons why I was engaged in HPSF from the beginning, because I think we need to come together more. We need to focus more on a few technologies. That doesn't mean we just need one to address every problem, right? But it does mean we don't want 100 to address the same problem. And I think that's still a big concern of mine.
All right, thanks. Okay, next up we've got Michela, and she is remote from Tennessee. I don't know where you want me to put your image, Michela, over the QR code or over something else, but I'll make you a little larger. Oh, are you muted? Are we getting audio from Michela? You're hearing a little bit. We're getting like a little buzzing over here. We had this working before. Oh, can you turn up your mic, Michela? Yeah, you can hear us. We just need your volume to be up higher. I'm gonna try. She's not muted. Hey, Michela, we still can't hear you.
You cannot hear me?
Yeah, can you turn up your mic a bit?
I am, and I'm almost, I can hear you very well. So what about now?
Oh, there we go. All right.
Okay. Oh my goodness, thank you so much. I've already spent my 5 minutes.
Okay.
And I really wanted to be there, but the weather, it's not so bad actually. I don't know why they canceled my flight.
I think everyone just
Anyway.
noticed you arrived. I think it's yes. It was very loud when you turned up your mic, but it's good. It's good.
Is it too much?
No, it's good. It's great. They equalized you. Yeah, go ahead.
I wake up everybody. Well, I'm an academic, first of all. So I'm at the University of Tennessee, Knoxville. I'm a professor, and I lead the Global Computing Laboratory. So as an academic, I feel I'm a researcher, a developer, a collaborator, and I'm also an educator. And my area is in HPC workflow, AI-enabled scientific workflow. And in this, I work with several of my colleagues at National Lab and experimental facility. I will tell you a little bit more about that. So said that, what is that the HPC software most pressing problem from my point of view is that so far it has been extensively focusing on simulation-centered workflow. So it's everything about simulation or predominantly simulation. And we are really at a turning point in which simulation and compute is no longer only the major pressing problem, but we have a combination of compute, data, AI, and I put another player here, which is experimental facility that plug in our supercomputers, that should plug in our supercomputer in a digital twin environment. So far they have been considered in isolation, or most of us have been considering them in isolation. We need really to work hard to integrate them so that the software ecosystem is addressing all four of them: compute, data, AI, experimental facility. When experimental facility, I don't mean frontier or El Capitan. I really mean about spectroscopy, X-ray, big experimental facility that generate data and integrate computing where the experiments take place. So a little bit different from the message of Martin and Christian. But at the same time, what is common to all this discussion is that we had heterogeneity, not only of the hardware, but also of the facility that collect data and compute. So said that, I'm done with my 5 minutes or less.
Right.
And I'm looking forward to discussing with all of you.
All right, thanks. All right, next is Brian. Do you want to
I
start?
hope you could hear me.
Yeah, we could hear you.
'Cause I
We can hear you
cannot
great. It's really good now.
All right, hi, I'm Brian Van Essen from Lawrence Livermore National Lab. I have a couple roles here that are important for...
Yeah, that was not an easy connection. I cannot hear you, so I hope you can hear me.
Hold on, are we muted?
We can still hear you.
You can hear us, right? Oh. Can you hear us? All right, I'm going to just mute Michela for now.
All right, so I'm Brian Van Essen. I work with Todd at Lawrence Livermore National Lab. I am the Livermore lead and point of contact for infrastructure on the newly announced Genesis mission, particularly with a focus on the American National Security Platform. This is what the 3 NNSA labs are deploying in partnership with the American Science Cloud that some of you may have heard about. And so, the goal of Genesis mission is really to create a platform that gives a 2x productivity in scientific and programmatic development. And that's going to, basically, we have to deploy a common place where we can bring our researchers and scientists together and maximize sort of the amount of science we can get for a fixed amount of government investment. Along those lines, one of our key concerns is how do we have a portable platform that can work across HPC vendors and AI vendors, but avoids vendor lock-in and sole source solutions, which can have detrimental effects over a 5 to 50-year program as you think about how long the national labs have been doing computational-based stockpiled stewardship. Because of that, we really think that open source software is going to be at the core of many of these needs and applications. We're looking heavily to them to help us build the platform, but that doesn't go to say that people can't monetize and make businesses out of this. So when you think about companies that have monetized the support and enterprise capabilities of open source platforms, that's absolutely a reasonable business model going forward that we can engage with. And of course, Genesis mission is highly focused on public-private partnerships. The second role I have is I'm also in the Advanced Technology Office with Todd. I'm the AI lead for how we think about future generation HPC centers. And so what comes next after El Capitan? And just again, for all of our leadership classes, how do we grow where you don't just necessarily have one massive deployment and then nothing for 7 years? How do you compose AI systems and capabilities into leadership class modeling simulation platforms? So what's the biggest challenge? Well, I couldn't pick one. There's a couple. One of them is the velocity. You hear about this a lot in AI, where things are changing daily, weekly. Sometimes you get multiple drops per day of new AI capabilities, and these have to be coupled with modeling simulation codes that last for decades and have critical mission needs. They're verified and validated, and we can't just drop them and replace them with a surrogate model. So how do we blend those two ecosystems where AI is actually not going to be driving our quote unquote business model in the national laboratories? We're doing science, we're doing program, and that really requires a certain understanding, modeling simulation is good and it gets us its ground truth for many things where we don't have experiments to validate it, and we don't just throw that away for AI. So properly maintaining open source software requires a substantial amount of work from research teams. What happens if you have researchers developing new capabilities and they get it to work for them, and that's okay, but if you want it to be a broadly supported thing within the open source community that works for more people, it takes more effort. And it's really hard not to just fall into silos where you have, you put out your patch, your fix, your little tool that works just on your platform, but does not cross any other platforms. And there's a whole ecosystem from how we reward people to how we think about supporting teams when they want to go that extra mile to make sure it works, doesn't just work on an NVIDIA system or an AMD system, but works on both concurrently and both effectively. And then finally, talking with Andy Warner, this is probably from him, I think he said, AI is HPC, but HPC is not AI. HPC is a superset of that, and it is absolutely going to be fundamental. If you think about, outside of large language models for natural language processing, which are really good and useful for things, anywhere else you go in the sciences, we need custom bespoke models that work for our platforms. Everything from, how we do modeling, simulation, and design, and we have AI-driven campaigns, to things like OpenFold and AlphaFold, where there's fewer, there's fewer modeling simulation tools, but there are HPC applications, and so AI will be something. It's not going away. It's like high-performance math libraries. It will not be everything in the national labs. So the standards are critical to evolution. Thinking about how you do reproducible science with half of your toolkit is changing, again, day by day. Also, how do we think about how these models can survive political or industry agendas, and how we actually have an enduring capability is really important to think about. So I'll pause there.
Thanks. All right, and finally we have Mike Heroux from Paratools.
Thanks, Todd. I'm semi-retired, so a lot of this here is stuff I've done, but I've been involved in a lot of open source projects over the years. I believe I've been the first person to utter each of these names here. The funnest one is Flang, because I have almost no involvement with the project, but I think it was the first person to argue that it should be just a capital F and not all capital letters. Anyway, so some of the biggest challenges, there are so many, right? In fact, part of why I like being semi-retired is because it gives me the chance to try to keep up with everything that's going on. There's so many changes going on. But I think among them is, we're used to parochial, hard-to-use, bespoke software ecosystems in HPC, and we really do have to move to ubiquitous, turnkey, and commoditized. And why I'm so excited about HPSF is I think it can play a central role, probably the central role, in realizing that as we try to make the modeling and simulation tools that we provide, the things that are going to be a big part of so-called world models, our codes are part of that, right? The key things. And if we do this well, getting our codes out to many people who need to use them and have them be, in a sense, invisible in the stack, but available, we will have a lot of success. And more success than we've had in the past, because I think the market for these capabilities to ground AI models in simulation truth is really, really important. Some of the challenges associated with that is getting the AI-centric community to pay attention to what we can provide. I think that's really, really hard today, because they're chasing big bucks in the large language model space right now, and paying attention to this modeling and simulation thing that feels like it was so, exascale, years ago is a big challenge. But I think they need us, and we know that, and we need to be ready for that. Also, I think we need to do a better job of making our software capabilities discoverable by AI. And so I've been doing things like, I'm just learning terms like skill.md files and things like that, right, where you try to encode knowledge, expert knowledge, and then make that available through some kind of semi-standardized technique so that agents can find these capabilities and descriptions of them. And it's not just technical. I think there's a huge part of this is cultural. We have to, we're used to in HPC to have been kind of the prima donnas. We had these high performance codes that did the latest, greatest science, but now we're not that anymore. And so we have to get used to the fact that our stuff is going to be embedded deeply into a software ecosystem that we don't control, right? We contribute to. And a lot of times our codes are going to be run on 1 or 2 or 8 GPUs, not across a huge machine. But we should be okay with that. And then also the culture of the AI community we need to be able to get their attention. I know we're trying, and none of these are binary kinds of things. But the more that we can get the attention, and the more earlier we can get them to say, hey, you really are going to need us, help us be useful to you, I think the better off we'll all be. Thanks.
All right, thanks. All right, so we have some additional questions for the panelists. And Michela, can you hear us now? I'm going to unmute you. Can you hear us, Michela? Let's see. Not that. Okay. I'm not sure. I'm trying. Microphone noise removal, personalized audio. I'm going to use same system. Can you hear us now, Michela? Oh, no, not that. Hold on. Can you hear us now, Michela?
Yes, I can.
Okay, great. We got Michela
Thank
back.
you.
Okay, your keyboard is really loud, so we're working on the audio here, but we're glad you're here. Okay, so we have some questions for the panelists, and I think some of them may have been answered by their initial spiels. They were supposed to give like one challenge, but everyone went for it. So we'll get into it. So we talk constantly about integrated HPC AI workflows, but coupling large-scale deep learning with traditional HPC simulations is notoriously brittle. I think everyone mentioned the need to integrate the two, but what in your view is the biggest bottleneck preventing AI and HPC integration today, and who ought to solve it? So I think let's give Michela a chance to start.
So a big challenge is to change our way we code, our way in which we think, and also it's a cultural challenge probably. Meant as that we need to better work with those colleagues who have developed the AI models, and at the same time we need to see the coding in a different way. It's no longer just who is the most talented in defining correct code, but it's who is more capable to think about how to train models that can serve as our companion in coding.
Okay. Brian?
So, okay, I would break this down into, there's at least 3 categories we should discuss here. There's sort of knowledge retrieval with general language models, which is an absolutely useful thing, but not in scope for this question, I would say. There's coding agents and sort of how do you develop new codes. Again, super interesting, critical part of how we do business, not really this question. I think about models that are coupling modeling simulation with HPC as the real hard part. And so, as I said, you can think about agentic workflows, and for the most part, if you take them out of natural language and go to domain sciences, they're actually still pretty bad. But the addition of HPC tools can make them quite good much, much faster. And so you need this coupling. So there's the whole velocity of the 2 different worlds that I mentioned that's a problem. The other one is precision. For many language models, you can get by with inference in 4-bit precision. That's great. If you think about domain-specific models, especially when you're dealing with out-of-distribution data, which they don't do well with Wonderful at all, but you often get into models that actually require, for surrogates and for other areas, they require a higher precision than the AI LLMs, but not necessarily FP64. So you have this interesting interplay between FP16 and FP32 that's critical when you want to represent, fields of, where proteins have folded that are very different from the commercially successful AI models, and then how you bring them together for the modeling simulation is going to be a challenge.
Okay. Anybody else want to add to that?
Yeah, I want to actually a question. how can something be notoriously difficult if we only have been doing it for like, 2 or 3 years or something, right? Like when I think back, when we started Cocos, 2 or 3 years later, almost nobody knew anything about Cocos yet, right? And I don't think we know how to do this, right? We haven't been trying this long enough to figure out, all the problems we're actually going to run into, right? The number of people who actually run or have been trying to run this in actual production environments is, approximately 0.
Okay,
right?
I take it back. I'll reword the question. We could just say coupling anything with HPC simulations is notoriously brittle.
That is true. I mean, coupling.
That's been true for decades.
Yeah, exactly. Coupling even HPC things with each other is notoriously difficult. But what I'm saying is, we are really, really early in this world, right? We don't really know yet what we don't know, right?
So I mean, based on that, I think that's true, and so I think actually not too worried about us tackling the technical challenges because I think we have the right people together. I think it's a communication problem to some degree because you have different communities that speak in languages. They have, as Brian said, different speeds. We have to catch up. The HPC is slower than typically the AI community, and so catching that, getting the right terminology, getting us into a room, and getting combined. I think this is really the big challenge. And once we have that, and we have this common understanding, I think the technical problems we can solve. I have trust in that.
I think one of the difficulties in general is the financial model. Brian, you mentioned, I think, public-private partnerships, and I think they can help, right? Hopefully they can. But I think it's been a real challenge to be able to invest in a product. The research team has a certain set of skills. We do have research software engineers. That's great. That's being added to teams. Even so, though, I think the whole financial model of how our project's funded is a real challenge. And in order for someone to use our stuff, they want to trust that it's going to be around. Mm-hmm. And that's always a challenge, has been traditionally a challenge in our community. So those are some of the things.
Okay, let's move on to the next question. All right, open source is the foundation for most HPC simulations, even proprietary ones. Use cases are multiplying, and with them, the maintenance burden on developers is skyrocketing. So this is getting to Mike's point. How do we prevent developers from breaking under the weight, and what's the single biggest thing that HPSF can do? Who wants to start?
I want to start.
Okay, awesome.
Because I've been supporting and really believing in open source for the past 20 years, which is how much I've been in the domain. And now I am posing and questioning whether this model is sustainable with the changes that are a fact nowadays, correct? So the open source exists if there is a business model in which there is an investment from institutions, from states, from federal funding that support people like us to create the open access. But now, if we reconsider this model, which is what we are doing nowadays, can we consider the business model of supporting software development and research in general? So if we go back to revisit that, then one of the priorities that is communicated to us is that industry have to participate in this funding. And so, again, open source is dead unless there is a sustainable business model in which somebody invests. And with somebody was, once upon a time, state, institution, federal funding. Now they point the finger to industry, and so industry should, in my opinion, have a more active role, a more decent role, because even if they claim that they don't need us, at the end of the day, many startups, many ideas that are nowadays billions profitable came from open access. And so this conference is very important because bring us together and bring industry together with us. And we need to have a very sincere and open discussion in industry. Do they enjoy open access? Do they use our software? They have to put something on the table.
All right, anybody else? Go ahead, Christian.
Yeah, so over my, more than a decade now on the Cocos project, right, one thing I've seen is that the shift to more software engineering focus, right, has been very dramatic, right? Like, I think if you want to produce software, right, which is actually being able to be used by hundreds of projects around the world, right, with, maybe even hundreds of organizations around the world, right, your work partitioning is going to be, somewhere like 80-90% software engineering and maybe, 10% research, right? And we in the HPC community, or a large fraction of the HPC community, has not been set up for that, right? If you support users, right? If you support production software, if you support, all the requests coming in all the time, right? On all these different platforms, with all these different tool chains you need to support, right? You don't have much time writing papers, following new research ideas, etc., right? You need dedicated teams for this. And, as Mike said earlier, right, the question is, what is the financial model for this, right? And I think we have some places which can do that, right? The NNSA labs can do that, right? CEA can do that. The facilities in the Office of Science labs can do that to a degree, right? But it is hard, right? And we need to find models where we organize ourselves as partnerships between, say, people working at the labs, right, and people working in universities, people working in industry, to sustain this software we need.
And I think a fundamental issue behind what you're saying is the fact that traditionally we've received money for novel research, right, and not for sustaining capabilities that are already present. Putting things in the open source is great, but you can often have this, what's called, I think, the tragedy of the commons, where everybody uses something, everybody sees value, but not enough value to sustain it in a robust way. HPSF is doing a really nice job so far of, creating the promise of sustainment of, the commons. But it's a real problem. We see this in publishing, where open access journals now, like ACM is moving to open access, has and the financial model for that is you need to have institutions contribute funds so they can keep going. But everybody sees, well, hey, it's free. Why should I pay, right? And similar kind of thing for open source. We have to. This is a social science problem as much as it is a technical.
So I think there's an education problem here. So I would argue that much of the most interesting science right now is team science, where you're not just a bunch of computer scientists, you're bringing domain scientists. And I think there's a huge education gap in how to do, small to medium-sized open source projects well with collaboration. So when I started at CMU as an undergrad in 1994, there was a Wednesday night class. It's called C Unix Survival Skills. It was like, how do you write a good makefile? Right? I don't see a lot of that in modern education. How do you actually do good version control? How do you do collaborations? How do you build that? At Livermore, we have an HPC 101 class, but again, we don't have a software development class, especially for our domain scientists. So as you work with these teams, there's an organic, you have to uplift your teammates one by one, but there's an opportunity here for us to, both at the laboratory level but at the university level, have these classes which are in some ways so mundane and yet fundamental that people just sort of assume that you come in knowing how to do this, and there's a discipline to it.
So I think this is a very good point, and I think the education component, basically, and how to do this right, is key, because a lot of people reinventing the wheel every single time and look up the same thing and then do different mistakes on it, right? But I think the next step is also to take it out of the teams and do it across teams, because the team alone won't do the problem that Todd has with the multiplying of the use cases. So you have to find common use cases and share the use case, and that's, I think, where HPSF can actually really help. And we need to actively agree to drop things and say, this is perhaps not the key thing for the larger community, because if we always want to support everything, we're not going to get there.
Although I think that so I would no longer try to go write a makefile. I would just ask ChatGPT to write, or Claude Code or whatever, to do that. So I think we also have to integrate tools into this process, right? And hoist up, well, what are the things that these tools can't do for us as part of the education?
Yeah, but even as these tools become more and more capable, you still need to understand what they're doing.
Oh, absolutely.
So,
no, I agree. But fewer people need to have that expertise, I think. I don't know. We have to learn, right? I think we have to learn.
I'm going to hijack the panel. I'm the moderator, but I'm going to say something. I think it's actually challenging because code review is more important. And and you are asking something that maybe knows makefiles better than you to write a makefile for your project, and you have to know whether it was correct. And that's been the challenge for me, is like I see that the model can come up with a solution, and I don't see that it's necessarily maintainable.
Well, one part about this is that to get these models to come up with something good, you have to really specify what you want in a clear way. If you, I mean, the Super Bowl ad was the stupidest one. Make this spreadsheet more whatever. He had some word there, some adjective that was just absolute garbage, right? If you just say, make my makefile cooler, like, it will not do anything useful. And so the advantage of using agentic coding is that if you do it well, you end up documenting the design process way more effectively to get a robust tool. Absolutely. And that can be reused, especially across teams. But that still requires people to understand what they're even asking for.
Sure.
Okay.
It's part of the story.
Yeah, absolutely.
All right, we're running a little low on time, so I'm gonna move to the next question. All right, for integrating, so HPC centers need to integrate traditional batch workloads with service deployments, and we'll have more on this in some of the other panels. But can we support both on the same infrastructure? What are the software gaps at the facility level, and how can HPSF help? Anyone? Did I?
We have to use AI factory stacks.
Okay. Any others?
I mean, we have to, like, batch processing is not a bad word. It's not going to go away, and it shouldn't be viewed as like some legacy thing we need to just get rid of. But we do have to have the integration point between them. One thing I'll say is I don't know a whole lot about Kubernetes, but I keep learning. It should not be magic. There should be robust ways to deploy these at scale, and that actually does not exist in the open source. There are proprietary solutions, but getting that to work robustly is hard.
The more we can adapt to the AI factory workload approach, workflows, I think the better off we're all going to be. You know, spot instances, being able to take decouple ensembles. So because a lot of times we use this massive MPI communicator to manage not only core physics but many ensembles. We shouldn't do that anymore. We have to move away from that if we want to fit into the new world.
I'm going to foreshadow the next panel, because I mean, this is actually something that goes to your point, Mike, because earlier you were saying that we need to make the AI people need us. And I think batch workflows are actually one of the places where they do need us, because the stacks, the AI factory stacks, Kubernetes, like all the job scheduling there, is not as good as what we've got in, say, Slurm. And a lot of AI factories are using things like Slurm, and actually Flux was integrated into some of the documentation for one of the major workflow engines. So stay tuned for the other panel for some more on that. All right, any other answers to this one?
Yeah, one interesting thing is that I feel like we have one area where we're actually already touching in the more cloudy kind of world, and that's our CI, right? Like if I look across our projects, you know how we are doing CI, right? We are not doing that in the traditional HPC deployment model anymore, right? We actually are using the classical kind of cloud environment, right? Everything is in containers, right? We have like, GitHub actions and stuff like that, initiating workload, right? We have some agents looking for changes coming in on the repositories to start, all this kind of stuff. So we have some touch points already, it's just that it's not like how we run our actual, workloads in the end at the application level. It's just, but I think we need to expand on that, right?
Mm-hmm. Okay. All right, last question. All right, increasingly, the HPC market is driven by the needs of the AI. Are we facing a performance cliff for traditional HPC? What software abstractions are needed to bridge the gap between where hardware is going and where HPC needs to be?
Well, two things. For one, reduce precision, and having libraries for reduce precisions, and having good reasoning of when you should use precision where. I think there's still a lot of experimental stuff going on. I think that's something where additional software could certainly help. But then on the other hand, I think also we're seeing some first signs that actually even in the pure AI community, there's a need for some more HPC, particularly AI for science. And I think actually perhaps it's not as dire as one could think about a couple of months ago. So I'm hoping at least it's getting a little bit better.
Well, I think ECP actually did a lot to move the needle on performance portability, right? And the applications, libraries, and tools that came out of that are generally speaking performance portable, but that's just a very small part of the whole collection of these things. We still have major libraries and tools that can't do mixed or multi-precision. They have to compile to one precision, right? And these are real challenges.
Yeah, one thing I'm wondering, as you just said, is if this situation is actually a bit more akin to, or going to turn out a bit more akin to how resilience turned out, right? Where we were very, very worried that the hardware wouldn't be able to support it, and in the end, they did, right? And one thing to remember is that in HPC, right? Yes, we need 64-bit precision, right? But outside of our dense linear algebra stuff, we don't actually need that much, right? We need enough, to make sure that our sparse codes, can saturate bandwidth, right? But we don't need it at the level, at the ratios where AI flops are, right?
Yeah. You need selectivity. You need to be able to do mixed precision, and some things at higher precision and others lower.
Right. You can do that, right? But and the question is, how much hardware overhead is it, real estate is it we actually need in 64-bit precision, right? And it might not be that bad, right? And so it might be possible that we keep having that.
Michela wants to, she's got her hand up, so let's let Michela go next.
Yeah, so from my point of view, we need to redefine the training, especially at the academic level, in which we need to teach more computer system and HPC, because what we are seeing right now is that our curriculum is predominantly based on AI foundation, and then we have all our students that have no clue where this AI model run, how much energy, what are their performance, what are their costs from the point of view of data, and all this knowledge comes from a solid HPC/computer system training. And so, are we still needed? Yes, we are extremely needed, because we are those that provide this knowledge in people that are using AI. We are too modest sometimes. We are not facing the challenge of training in HPC and computer system because, I don't know, that is a big question, because it's too hard, because it is hard to teach, but I feel that there is a need for redefining what we are teaching. Teaching just coding is something that will become obsolete. Teaching computer systems that support AI will become predominantly needed, and we have a gap.
All right, Brian?
I was going to say, I think there is a real challenge here. I mean, we are going to see support for either hardware-based or solid or robust emulation of GIM and GIM-Vs in FP64. But overall, I think the trend we're seeing is that it's increasingly swamped by other hardware on the die that's going towards AI use cases. And so for some deployments, that'll be just fine if you have a nice mixed workload. But I think our ability to cite larger systems that are going to push modeling simulation, we're going to be increasingly either power or dollar bound. And we're going to get less system for the budgets that were allocated because it becomes a smaller and smaller part of the real estate.
And peak 64 for GEM has gone down, right? But Ozaki's around to fix that for a lot of problems. And then, but for where people really need 64-bit, still somewhat at least, is in sparse. And there you've got, it's all bandwidth limited, which is still going up. So
right, so there's a balance. So I mean, GIM is okay maybe with Ozaki, but there's all the vector operations as well. It is balanced by the bandwidth, and so as bandwidth goes up, we don't necessarily need to double. We need the amount of FP64 for vector to match the bandwidth. But the problem is the whole system just gets more and more expensive per chip. So in aggregate, the dollar, what we're able to buy is going to be a much, much smaller system for our mod sim.
All right. Any final comments? We have time for maybe one question from the audience. Anybody want to jump in here and ask a final question? Nobody, really? But yeah, okay. I'll run out there.
Okay, I have a quick question related to mixed precision, lower precision, and all that good stuff. So not that long ago, we spent a lot of time trying to support FP16, BF16, which already by the fact that there are two standards for it, makes you know I have a heartache about it. When we go lower, there is probably one way to do it per vendor, startup, and all that good stuff. I want to support it, but I can't support everything that everyone under the sun can imagine. We probably need to fix that, and what do you think how do you think we should go about it?
Get your code used by the AI community, and you'll have more money than you know what to do with to support every single version of the code. I don't know, that's a flippant answer, but in a way it's true. I mean, the reason why all these various hardwares exist is because the vendors can put that much effort into all these different variants for the applications that pay off. I don't know how you do it in a portable way.
So I think there is a start of an answer, right? Both in C and C++, we actually introduced extended floating point precision types, right? So we went away from just having, float and double, but there's, similar to the integer ones, right? Where we essentially introduced like int 64, int 32, int 16, int 8, and whatnot. And yes, initially everybody did their own thing, right? But I think if there's enough market pressure, and there will be, even from just within the AI community, a standardization around these types will work, and you essentially just going to choose your floating point precision the same way as you choose like integer width, right? And, yes, we need to write our codes, that they are configurable on that front, right? And you might need to not just have to have like a global, everything is this, everything is that thing, but you need to be able to more fine-grained configure it, depending on where you need how much precision. But that's probably the path forward, at least getting away from every vendor has their own complete different thing.
All right, with that, I think it is time for break. So let's thank our panelists, and especially Michela for joining remotely in a snowstorm.
Thank you, everyone. Enjoy the conference. Bye-bye.